All right, in this video, we are going to take a look at infinite and removable discontinuities and just some of the similarities and differences between the two. So when we look at these functions, or look at these discontinuities, we are really looking at rational functions, which is just those functions that appear to be a fraction. So for example here, this f of x equals 1 over x minus 2. So thinking back to working with domain, we know that we could say, all right, well, for our domain, if I ask you what is the domain of this function, we know that we cannot divide by 0, right? That is not allowed. So x minus 2 can't be equal to 0. So x can't be equal to 2. That gives us a domain of negative infinity to 2, union 2 to infinity, and obviously we're not including the 2 in either of those intervals. So now the question is, well, what happens at x equals 2? It's going to be a discontinuity. All right, this function is going to have a discontinuity at x equals 2. So there will be a discontinuity at x equals 2. And now the question is, well, what kind of discontinuity is going to occur at x equals 2? So let's just take a look at the graph of f of x. So here you can see on Desmos, I've just graphed 1 over x minus 2. And looking, we can clearly see that at x equals 2, we have some sort of infinite discontinuity. Okay, as I scroll up and scroll down, this line will approach 2, but it will never actually touch x equals 2. And so this is a vertical asymptote at x equals 2, and it is also an infinite discontinuity at x equals 2. All right, so this is going to be an infinite discontinuity at x equals 2, and that also means that we have a vertical asymptote at x equals 2. Remember that asymptotes are just these like dashed lines that we'll draw that we approach but never actually touch. So we could also say that we have a vertical asymptote at x equals 2. So that's how we can find our infinite discontinuities. Wherever we have a vertical asymptote, we are going to have an infinite discontinuity. And it's just when our denominator is equal to 0. So in this case, at x equals 2. However, there are some cases where it's a little bit different, where we won't have an asymptote even when the denominator is equal to 0. Let's take a look at one of those and just see when that occurs. So for this function, I have f of x equals x plus 3 over x squared plus x minus 6. Okay, we can note, well, let's factor our denominator. Factoring my denominator, I get x plus 3 times x minus 2. What I see here is that I actually have a factor that appears in both my numerator and my denominator. So you might think like, oh, I could just cross off the x plus 3's, and this is the same thing as 1 over x minus 2. Well, the graph is going to look very similar to 1 over x minus 2. However, x equals negative 3 is still not in the domain of this function, right? Because if I plug in negative 3 to this original function right here, you're going to get 0 divided by 0. That is an undefined number, right? 0 divided by 0 is not 1. It's undefined. So there's still going to be a discontinuity at x equals negative 3. It's just going to be a removable discontinuity. So we have a removable discontinuity at x equals negative 3. That's where we can cross it off. There's still going to be an infinite discontinuity at x equals 2, because x minus 2 still appears in the denominator. If you plug in 2, you're going to get a number divided by 0, which of course is undefined. So let's graph this. X plus 3 divided by x squared plus x minus 6. So parentheses x plus 3 divided by x squared plus x minus 6. And we can see that these two graphs are the same exact thing. However, my blue graph here actually has a hole at -3, 0. So if I were able to click, and I guess, oh, yep, I can click here. At -3, 0, we see that we have a hole, -3, undefined. So that is where our removable discontinuity occurs. Because if we were to plug in -3, it would give me both 0 in the numerator and the denominator. So that's why we have a removable discontinuity there. We still have an infinite discontinuity at x equals 2. Right? If we zoom out, we can see this is clearly an infinite discontinuity at x equals 2. And of course, we have a vertical asymptote wherever we have an infinite discontinuity. All right, so that's kind of our difference between infinite discontinuities and removable discontinuities. I hope that this was very helpful for you.